Okay, what I'm going to talk about. Since the last years, there has been a lot of evidence that Phonon hydrodynamics can explain some of the evidences that we can observe experimentally. And the usual point of view is that you have two different types of materials, one that is kinetic and the other one that is hydrodynamic. The usual one for the kinetic is the silicon and germanium, and the usual one for the example for the hydrodynamic regime is the graphite. Well, this talk is just to change a little bit this point of view, changing slightly from this image to this image. So my point of view is that the hydrodynamic is something that it can be a transition from one side to the other. So my point of view is don't think about hydrodynamic as something that it happens only in some kind of materials, but is more general. Just for the people who don't know me, most of you know me, my talks are not usually don't to explain the physics. My presentations are always to see my point of view. So from this side, my intention is that you understand my point of view, and by reading my papers, you will be able to find the full physics. So it's just a sketch to give our point of view. So, well, this has been, what I will present here is a set of experiments that we have done with a lot of people around the world. So there are several groups, experimental groups that work so hard with us in order to understand the physics inside the experiments. And what you are going to see is the final result of this of all this work. So on this point of view, this is the result of a lot of discussion. So first, I'm going to talk about the hydrodynamic regime, and I'm going to say that I'm going to show you that for silicon, hydrodynamics can help you to understand a lot of experimental results that, as you know, is not the typical point of view. People usually believe that silicon is a kinetic material and thus has nothing to do with a hydrodynamic regime. So I will try to convince you the opposite one. And then I will show you some new evidences that after that you can extract from other experiments. Then I will finish with some microscopic derivation. Okay, what is Phonon hydrodynamics? Phonon hydrodynamics, from our point of view, is that phenomena that it can be explained by this equation. That, as you can see, is the Fourier law. You can see here that it has a heat flux and a gradient of T, and other terms. One of them is the time derivative of the heat flux, and the other one is the Laplacian of the heat flux. This Laplacian of heat flux, from our point of view, if you need it to understand the results, then you are seeing Phonon hydrodynamics. It doesn't mean that it should be normal dominated. So from our point of view, is just if it follows this equation. Well, our point of view is, well, you can always use an equation to fit the data. So it's not enough to follow, to explain the experiments with the equation, but that we have an ab initio expression to obtain the parameters that we need to put in this equation. So if we are able to obtain by ab initio a parameter and then put it in this equation and explain the data, from our point of view, this is Phonon hydrodynamics. Okay, this is what I'm going to do in this presentation. First of all, why this equation is powerful to understand experiments, because you can use it as is a mesoscopic equation. You can use it in console, and you can do whenever complex geometry that you want. So this is a powerful point of view of our modelization. The other one is that we have a KCM model that allows us to extract these parameters to put in the equation. So this combination from our point of view is ab initio KCM, and this is what I'm going to explain. Okay, let's start. I'm going to show you that for silicon, hydrodynamic equation, it allows us to understand the size, the geometry, the temperature, and the frequency behavior of the thermal conductivity. There are a lot of experiments in silicon, and we have revised it from the point of view of this equation, and we have seen that with the same parameters, we are able to explain all the phenomena. First of all, the first of the experiments that I'm going to show you is the most simple, is the thermal conductivity of thin films. You can put a gradient of temperature in between two extremes of a thin film, and then you use this equation with the ab initio parameters. The ab initio parameter is the thermal conductivity for at room temperature, for example, is 150 meter Kelvin, and L, that is the non-local parameter. Let me go back. Non-local length, this one here, is approximately 200 nanometers, more or less. These are the two parameters that I'm going to use at room temperatures. Obviously, when you change temperature, it's going to change, but the calculation will be the same. Well, as you can see, the experiments are completely described by our model to a certain limit. You can see here in gray. You can see it slightly. The color is not very good to see it, but in some region, there is an exact fit between the experiment and the prediction. Well, which is the physics of this prediction? Where is the reduction of the thermal conductivity because of the hydrodynamic regime? Is this one here? Imagine that this is the thin film, and you have on the center you have the flux that is not affected by the boundary. But as you approach to the boundary, another scattering, that is the boundary scattering, is affecting the phonon. So it means that on the side on the boundary of the thin film, this heat flux is reduced. Okay, the reduction explained by the Guillen-Hansel equation, this hydrodynamic equation that I showed you in the other slide, is what is changing is the profile of the heat flux. So you have the heat flux that on the center of your structure is giving you the Fourier value of the heat flux, let's say the Fourier effective thermal conductivity, and as you approach to the boundary, the heat flux is reduced because of the effect of the boundary. And because of this Laplacian, there is a transition from one point to the other. And using this equation, the match is exact. Well, let's go back. Why we lose the predictability of our model? We have also an intuition of why is this prediction is loose, is because L is giving you the size of this boundary layer, let's say the region of your material that is noticing the boundary scattering. Well, as L is, or let's say, as the thickness of the film is getting smaller and smaller, there is a point where this layer can overlap with the other layer. And this means that you have couple of effects of the two surface. At that point, the system crashes. So at that point, the equation is not predictive, and we need something more, okay? So it's important, this example, because it, from our point of view, is not so it's also important having this limit, because in all experiments, as you will see, there is also a limit like this. So another way to observe that hydrodynamic is working is that when it does not work, it does not work at the same point. So these are the two points. Okay, you can also predict whole polysilicon films with the same predictability. And well, this is the heat flux that you achieve. So the heat flux is reducing in the boundaries and it's getting larger on the center. Okay, well, you can say you don't have any evidence of this profile of heat flux. You only have the effective thermal conductivity in the experiments. But you can do molecular dynamics to see if the hypothesis can be or not wrong. And this has been done well, we have done a work on this in collaboration with Luciano, but also Costas did the same work, that is calculating the heat flux on a wire depending on the position depending on the distance respect the center. And we have seen that this kind of profile, it's shown. So, and in this case, it's just molecular dynamics. So there isn't anything else that atoms vibrate. So from the point of view of the experimental evidence, well, we can say that if molecular dynamics is reproducing this and the experiment is telling you that the thermal conductivity is more or less the same, well, we can say that maybe this approach is good. Okay. Well, let's go to the second size evidence. So we have done a thin film. Now we are doing something else, that we have a substrate, and on the top we put a thin film. A wire, a metal wire that we heat, electrically heat, and then we see how this heat is released. Okay. Well, in fact, what we do is to heat one of the lines that you see here in red, and then by thermoreflectance imaging, that is this setup here, we're using a laser probe. You can obtain the temperature on different points on the surface and obtain the thermal profile on the top of your structure. The orange line is just a second line that we put there to compare with electrical measurements, just to check our results. So don't worry about the orange line. You just need to follow the green dots. If we try to explain this by Fourier, you cannot explain it by the bulk thermal conductivity of the Fourier. So this is not silicon, this is indium gallium arsenide, but in silicon you observe more or less the same. So this is just to show you the results. Okay, well, this is the bulk thermal conductivity. As you see, the temperature on the heater, it's under predict, and the temperature on the sides is under predict. No, is over predict, sorry. One may think, well, if Fourier works, you should obtain a fit of the thermal conductivity to fit these results, but this cannot be done. If you reduce the thermal conductivity, obviously the heater will heat up because it cannot release heat to the substrate. So you will heat the metal line, but you also heat the sides of your structure. So by changing the thermal conductivity, you will not get the results. And if you try to feed the other way, you will find the contrary. That is the heat, the temperature on the metal line will be under predict. So there is no gain for Fourier. So Fourier cannot predict this behavior. If you use KCM, you get exactly the combination of the two things that you need. You get an increase of the temperature of the heater, and you get a reduction of the temperature on the sides. And this is by using exactly the same values of kappa and L that we use in the thin film. We have used the ab initio parameters. So there isn't any trick, let's say. We don't use even, we don't also use any thermal boundary resistance. We just put the intrinsic thermal boundary resistance without changing. So this is another evidence that silicon can be explained by this. And we get something that as you get smaller and smaller, this effect of heating the metal line and cooling the sides, this effect is higher and higher as you go smaller and smaller in size. So let's say in the other way around, when you go to larger and larger sizes, you get to Fourier. And Fourier KCM gives you exactly the same prediction. Okay, these are the results for silicon. I could start by here, but here in the site, is a little bit more tricky because there is much noise here, but it's more or less the same. Look at this. These are the three thermal conductivities, and you cannot fit it. You cannot fit the whole thing with the thermal conductivity. Well, why this is happening? Because the Laplacian, so from our point of view, is that the Laplacian of Q gives you a kind of, let's say, inertia of the heat flux. Why is giving you this inertia? Because when you have a tiny structure, when you go down the structure, you don't have any scattering. You don't have any scattering, neither normal nor resistive. And as you don't have any scattering, heat flux should go downwards. And because of this, the heat cannot turn to the rate that Fourier laws force to do. So the heat flux, due to the lack of scattering, cannot fold itself to follow the temperature gradient. That's the whole stuff. That's more or less the conclusion of this thing. Okay, so from our point of view, well, our results show with a single L, we haven't done any fitting for the L. With a single ab initio of L, we have predicted the thermal or the behavior of these systems. Well, while in a kinetic regime, you would need a size dependence mean free path for the phonons that you use. So instead of fitting or putting an extra term, we have just a single term that allows us to interpret the result. Okay, let's go to the geometry. I will do this very fast. It's exactly the same system. So you have a metal line that is releasing heat on the bottom. But in this paper, what we have is just change the geometry without changing the size. Let's say when you have a 10 microns structure, and in one side on the right, you have a linear wire, and on the left, and on the right, you have a circular structure with the same size. The only thing that we have changed is the geometry. Well, when the system is large, you don't, both predictions are giving you Fourier, but as you get the reduction of the structure, you start to notice that there is a tiny difference between the linear and the circular. Well, this is not tiny, because as you can see in the linear case, you have almost Fourier. You have the prediction that is almost close, it's very close to Fourier. But when you curve it, you have something that is much different. Believe me, this change here is important. You know that in some kind of experiments, this difference can be very large. So look at this. The size of the metal line is the same. We have only curved the metal line, and we obtain a different result from one structure and the other. And as you get smaller and smaller, you get higher and higher difference between the linear and the circular. So from our point of view, this can be explained by, so the red is, obviously the red is KCM. KCM is capturing the effect of the geometry, not just the size, but the geometry. So we can get in the same equation, the two scales. Well, why this happens is more or less the same. You have the same, let's say, inertia of the heat flux, but in the case of the circular structure, you have another thing, that is when you have heat flux going to the center, then the heat flux should curve again to the bottom. So it cannot pass through on the other. So the heat flux goes to the center, curve again, and this extra curvature of the heat flux because of the geometry gives you an increase of the thermal resistivity of your sample. And that's the reason why the circular structure gives you a much higher resistivity or a much lower conductivity than the linear one. And it's because of the shape, not the size. Okay, what we have done here, this is from our point of view, this plot is the exemplification that Fourier law cannot explain this. We have done for each sample the fitting of the thermal conductivity to fit to the heater or to fit to the size temperature. And as you can see, for the same heater width, you have plenty of numbers. So you need a lot of thermal conductivities to explain the same size. From our point of view, this invalidates completely the thing that this is a phonon versus line width thing regarding thermal boundary resistance or something like this. So the powerful results that KCM gives you says that only a single L is enough to explain the results. Okay, let's move a little bit more. The next test will be to test the temperature change. So we have an expression for the thermal conductivity and the non-local length, but these values change in terms of the temperature because these values depends on the relaxation times of the phonons. But as you get to a lower to a lower temperature, these values should change. And look at this. We observe that the predictability is still the same. So when you go to 200 nanometers or 100 nanometers, when you go as down as 100 nanometers, you still can rely on the bulk, no, not the bulk, on the ab initio non-local length, L. At this size, the non-local length is approximately 2 microns. At 300 is 200 nanometers. Here are approximately, I think that is approximately 2 microns. And look at this. Once again, red line is the Fourier, is the KCM prediction. Blue line is the Fourier. KCM predicts correctly. These are the on the bottom. You can see the result, the value of the L for the different temperatures, and you can see that the dots and the figures are at the experimental values that we need, and the blue line is the ab initio prediction by our KCM. Okay, this is the full picture. You can get a prediction of the temperature, size, and geometry effects on the thermal conductivity with full of data. And all this data is predicted with exactly, believe me, the same L, just one parameter. And it's not fitted, it's ab initio. And from our point of view, this is a robust demonstration that Guyer-Hansel equation works better than Fourier. I'm not going to say that hydrodynamic, but Guyer-Hansel equation performs everything. Well, if you try to understand the effect of this metal line on the top of a substrate, you know that the usual point of view is to include a TBR. Okay, so you usually use a TBR because you say, well, as you have a tiny structure, this structure has an increased thermal boundary resistance. This is the usual point of view because the phonons that are larger than this size cannot pass through, and you fit the data with a TBR. And this is what in this work have done. You need a temperature-dependent TBR fitted to predict the results, while in our model, you just need the TBR to explain the Fourier limit, and the reduction of the thermal conductivity, the increase in the thermal resistivity is just due to this Laplacian term. And what I have plotted here is, you see in yellow, in yellow and in red, the effective thermal conductivity of the sample, that is the heat flux divided by the gradient of T. When you do this, you obtain something that is reduced near the structure, and when you go farther and farther, you go to Fourier that it should be the yellow one. Okay, but look at this. I want you to observe this just physically, that both models give you more or less the same. That is a reduction of the thermal conductivity near the sample. So in our case, we don't need the TBR because our Laplacian makes this effect, the effect of the TBR, and without using any fitting parameter. Okay, let's talk now what it happens with the frequency. What happens with the change in the thermal conductivity with the frequency? Well, for this, we have used the frequency domain thermoreflectance experiments. Let's see what is this for those who don't know this experiment. You just have a substrate with in the top you have a transducer. You hit with a pump laser that is frequency dependent, also it's time dependent. It has a frequency, the blue line, and then you observe the response of the sample with the proof. Okay, so you hit with a pump that has frequency dependence, and then with the proof you measure the temperature of the sample. And what you observe is two things. One of them is that the amplitude has a variation. So the amplitude is varying depending on the effective thermal conductivity. The lower the thermal conductivity of what you have on the substrate, the higher the temperature on the metal, on the transducer, obviously. Well, we have done this with Fourier and with KCM once again, and the response is different. Well, the other parameter is the shift, because there is a delay. Obviously, you have a delay and you have a change in the amplitude. Well, once again, we have made one check. We have tried to explain with the same model the shift and the amplitude here. On the top, you have the shift, and on the bottom, you have the amplitude. And what happens is that when you try to fit the amplitude, you unfit the phase. And when you fit the phase, you unfit the amplitude. This is exactly the same as in the previous experiment. So what happens is that the effective thermal conductivity that you need to fit the delta T is higher as you go higher in frequency. And the thermal conductivity that you need to fit the phase is lower. So once again, game over for Fourier law. So you cannot use two thermal conductivities for the same experiment. And if you do this with KCM, look at this, the solid line, you obtain exactly, for both of them, you obtain the correct value for both, for phase and for thermal conductivity. Once again, you have a limit of validity, once again. And it has to do with the relation between the L and the penetration depth. Now, I don't want to go into the details, but the nice thing is that it fails to predict the thermal conductivity on the same point, where more or less the L is of the same size as the penetration depth of your experiment. Okay, once again, you need a frequency dependent thermal conductivity. You need to change the thermal conductivity with the frequency, and in this case, you just need a single L. You don't need to change anything else. Well, now, okay, I have shown you more or less the four evidences that from our point of view are the ones that show us that hydrodynamics is better than Fourier. And now let's going to see how can you obtain Phonon hydrodynamic from BTE if you only if you are working with silicon, because in silicon normal scattering is not high. So you cannot apply the same result as in graphene. So you need something else from the BTE to justify that you are using the hydrodynamic equation. And well, this has been done by this colleague, Juan Camacho, that is an extraordinary guy working with the BTE. All the results that we have done here is in collaboration with these two. So instead of working with the BTE, we are going to work with the moments of this BTE. You know, if you have a function, you can work with a function, or you can work with the moments of the function. It's just a change of basis. So you can work with both of them. You can have energy projections, so energy integrated moments like this, the mean energy, or momentum integrated moments like this one, that is the thermodynamic momentum. It's the integral of the momentum of each phonon. You have these two kind of averages, and you can work with both of them, but not only with them, but with all the higher order moments respect. So if you take in consideration the exponent of this integral here, so you have the different velocities. So if you work with this, basis is like changing from the world of the phonons to the world of the moments. Okay, this is our point of view. Well, you can say, well, it's the same. You have infinite phonons. You can change it by infinite moments, and you have the same problem. And the question is that you don't have the same problem. I will explain why. The usual answer for the normal, the usual answer for the phonon hydrodynamic is that momentum is conserved. Okay, so you have normal collisions that don't destroy the moment, and you say, well, as you have this moment, the system cannot behave kinetically, and you have hydrodynamic. Well, this is part of the story. This is just part of the story. You have to finish the sentence. That is, as you have momentum. Well, why I say this? Sorry, because if you believe, so if you think in this sentence, if you don't have any collision other than normal collision, you should get an infinite thermal conductivity, because you need resistive collisions in order to have a reduced thermal conductivity. So this is just a part of the story. So at the end, when you have this distribution function, that is the usual one that you use when you have a momentum conservation, that the correct way to explain it is as the collisions, as the most important collisions are conserving the momentum, the destruction of the momentum is slow. That means that when you have a momentum on some part of your system, the destruction of this momentum is slow respect to the size of your sample. And then is when you say, well, at that point, my distribution function should take in consideration that I have this momentum. And that's when the system shifts to that point, okay? But look at this. This reasoning does not prevent from applying from any other thermodynamic magnitude. You can have something that instead of, let's say, conserving momentum, you can have that the slow thermodynamic variable is the heat flux. It's the same. If you have a heat flux that is reducing slowly, this heat flux should modify, should shift to something else, the distribution function. And that's our point of view. Instead of having these answers, we will have something like this. And not only this, well, in this case, when you apply this form to this BTE, you will obtain this equation, the one on the bottom. And at the end, if you are in the steady state, the first derivative go, at the end, you will get the Fourier law. So at the end, you will get the Fourier law. If you get, this is the usual, this is a standard BTE way of working. So I'm not explaining you something that you don't know. Well, if you change the collision term by something like a relaxation time approximation, is when you obtain beta, that is the thing that you need here. Well, but what happens in a system like this? You can say, oh, well, once again, you have a flux that it has some kind of inertia, and it has a relaxation time that is slow enough to shift the distribution function. But there are other things that are slow enough. And one of them is the gradient of Q. The gradient of Q cannot change as the way that you want. It should be according with the relaxation of the phonons that you have inside your sample. And if your phonons are not colliding enough, then your distribution function, when it's cured, should change to something that, let's say, in this way, maintain this curvature, okay? And that's the reason why we use the distribution function that grants us that the thermodynamic magnitudes that are conserved, pseudo-conserved, not fully conserved because they are decaying, but not fast enough to think that they are finite. And that's our point of view. When you put this and you do exactly the same, I will not go into the details. You can read it in our paper, our PRB paper. It's not here, but I'm sorry. Well, if you do this, at the end, you will obtain the expression for beta, G, and you will put it here, and you will obtain the thermal conductivity, the L, and the alpha of this equation. And that's the way as we proceed, okay? So this equation is the one that grants the proper conservation of the thermodynamic magnitudes that are important in that experiment. So if you have other magnitudes that are not fast enough, you should impose it in your answers. And that's our expression. Well, these are the values of the L, of the non-local length, and the experiments are the dots. So as you can see, our experiment, it seems to work. Okay. Well, once again, let's compare RTA, typical RTA, with our model. In RTA, if you use RTA to solve the BTE, it's usual to think that you have phonons with a mean-free path that on the left here, you have lambda, capital lambda K, that it means the mean-free path of the phonon K, and you compare it with he, that is, let's say, the inverse scale, the inverse length scale of your sample. And the typical point of view is this change. So in each size, the phonons that are larger than this size will be removed, and the other one will pass. And this is the typical point of view. But if you're doing with silicon, you will get, in 300 Kelvin, you will get a reduction. These are not length scale, but believe me, you will start to see effects from this theoretical point of view from 30 microns. 30 microns, it means that if you have something that it has 30 microns, you should observe a reduced thermal conductivity. And this has nothing to, so this does not agree with what we have seen. The point where you start to see some changes are at 1 micron, not at 30 microns, as this experiment predicted. And if our proposal is, instead of doing like this, let's say that this Laplacian term, this lambda square he square, be replaced by our L square he square. Well, how can we get this? It's just get the Wheeler-Kohatzel equation, Fourier transform it, and algebraically group. And this is Q plus L square Laplacian of Q. So this means that this reduction of the thermal conductivity is local. It depends on the position that you are measuring. And if you go to points or places where the Laplacian of Q is very large, you will get a reduction. But if you go to places where the heat flux is not curbed, you will get the bulk thermal conductivity. So we propose to change from something that is global to something that is local. We believe that this is the correct way to interpret our experiments. Okay, the other thing is that I have said that we have a limit of validity of our model. And this means that when you go to very small structure, you will get incorrect predictions. And what we have observed is that when you plot this is delta F, it should be this minus the equilibrium one. When you plot delta F, depending on the size, on the mean-free path of the phonon, you will get a lot of phonons with negative value of delta F. For F, not delta F. We will get negative values of F for the phonon, and this is impossible. It means that you should have a negative number of phonons. And instead of this, well, the thing that you see on the bottom on the green plot are just numerical errors, but the important thing is that the blue thing that you see here. the conclusion is that the limit of predictability is that when you go to a very small thing, you will get negative values of f. And then you should revise out the model because it's telling you something that isn't physical. Okay, how much time I have? 5 minutes. 5 minutes, okay. I will go very fast. Once we have tested the micro and mesoscopic, macro and mesoscopic, micro and mesoscopic models, let's see if we can interpret something further, so something else. And we have done it in collaboration with CU Boulder, with the Margaret Murnay group. They have these metal lines that are excited with just a pump proof, but with ultraviolet. So they have a very large precision, so they can go to 20 nanometers. So the using of ultraviolet is to go to a very reduced size, and they heat very fastly. And this metal line heats up to a rate that it starts to vibrate. And it has a couple of physics. So they have the coupling of the elastic waves and the thermal relaxation. That the thermal relaxation gives you an expansion that is decaying because the heat is released. Okay, so you can have the both physics. The important thing of our model is that we can do it with COMSOL. So we can combine with elastic module, and you can hit the plane. That is something that you should do it with caution, as Luciano says in the previous presentation. And look at these. These are the prediction of the KCM in blue and the experiment in black. So it's okay. There are some divergences like this, but you can obtain these nice results. So we can use it, combine it with elastic module. So it's powerful enough to go to such a complex experiments. And the prediction is very good. Okay. This is the hydrodynamic region. This is the region where the Laplacian is important. Now I will skip because I don't have time, but the important thing, the most important thing is that in these metal lines, when you have this experiment and you can go, look at this, you can go to picoseconds because this experiment is super. You can go to some picoseconds. What we observe, look at this. Once again, Fourier is not working. So Fourier should give you just a single decay with, at the end, a power law. This is what Fourier is giving you. You cannot get something else from this. And what you get is that you need a double exponential. You need two exponentials to explain these results. You cannot do it with a single exponential. This is the best fit. So this is not using the Fourier bulk. No, it's fitting the bulk, fitting the TBR, fitting all the stuff, all that you can do to fit the experiment with the Fourier, and you cannot get this double exponential. And because in our case, as I will explain you now, it has something more, we can explain the results. What do we have? We have what we have called the two-box model. This is what we developed to understand this sample. Just the little story. You have two different resistivities. One that is the TBR, between the metal line and the substrate, and the other one that is due to the Laplacian. These two has two different time scales. One of them, it has to do with the TBR, and the other one, it has to do with L. And this is our interpretation. At the very beginning, you have that the Laplacian is 0 because you don't have any flux. You have a decay here that is just because the TBR is very fast, this one here. And once you get a complete balance between the metal line and a region on the bottom that we call damp region, so there is like an image of the metal line on the bottom, and when you have equilibrium between them, then you start to see the second time scale that is due to the Laplacian of Q, and that's the reason why we see these two time scales. The first one that is the TBR, and the second one that is due to the Laplacian. And we have done it for a lot of line width. And here you have the TBR time scale. And here you have the hydrodynamic time scale. When you go at very reduced size, the hydrodynamic, at very large size, the hydrodynamic goes down to 0 and you get to Fourier. And when you go down in size, you start to see the hydrodynamic effect higher and higher. Well, just to point, the usual experiments working on this kind of materials and metal lines used to work at start the analysis at 1000 Kelvin. I don't know why, because some of them can go to some picoseconds. I suppose that is because this second exponential cannot be obtained if you fit the Fourier law to explain this, that from our point of view is hydrodynamic. And just to finish, just a couple of minutes. Most of you know the work that Sebas has led. That is, we have obtained a phonon hydrodynamic, let's say, second sound in germanium. Well, he has the super idea to focus directly the laser on the metal, on the germanium, instead of using a transducer. And the thing is that when you use a transducer, you get what I have shown you when we revise the frequency-dependent thermal conductivity. This is the usual thing. But as you get to high frequency, you get like a go back of the phase to fit the thermal conductivity. So you get a reduction of the phase. Well, what does it mean? Well, I will not go into much of the details. I will just explain our point of view of why this is a second sound. Is just imagine that you just have a diffusive behavior when you hit with a pulse, and then you go back to 0 in the heating. If it's diffusive, you will get the maximum of energy on the point where you hit. But if you have second sound, what you have is if you hit with a pulse and then you go back to 0, you will have a pulse that is going down. And what you get on the back of your pulse will be a 0 temperature. So you will get a 0. That's the reason why you get something that is in phase with your sample, so with your pump. So you hit with a pump and the heat is going like a wave, and then you go back, you go down to 0, and you see that the temperature has dropped because the temperature has gone with the wave. Okay, that's the result. This can also be explained, but as I don't have much time and Sebas is here, maybe we can discuss with those who wants to know more details on this. But well, one of the things that I have to say, and that is that they, Sebas and Ricardo has helped us a lot in make us see that is not only a Laplacian thing, that is an interplay between Laplacian and the tau and the derivative of Q. And without this experiment, we wouldn't be able to understand such a cross effect, because it's very tricky. If the Laplacian is very high, this is removed. If the Laplacian is very low, this is increased. And the nice thing is that when Sebas hit the hit on germanium, as the penetration depth of the germanium is very tiny, it's like removing the Laplacian. So it's something magical that with this brilliant thing we have been able to explore. And well, that's all. I hope that I have, let's say, combines, not that hydrodynamic is the best thing, but combines you to read our papers about all this stuff on silicon. And well, I want to be, I'm very grateful with all these guys, Alisa Curry's group at Purdue, Margaret Bundain's at Boulder, Sebas and Ricardo, obviously, they are very important to us. And these are, this is our group. Albert has done all the COMSOL stuff. Luke is the student who has done the ab initio calculation. And Javier is is a super guy for the continuum model, continuum modelization. And Juan has a microscope in their eyes to see BT behavior. So they are super guys. Without them, this has not been possible. So that's all. Thank you very much.